Welcome to Lecture Online, and now we're going to take a look at Gauss's law in a different way. A lot of my students always ask, why do we have to put spherical or cylindrical Gaussian surface around our charges? Why can't we just put a cube around our charges? And here, this video is made to let you know why you shouldn't try to put cubic Gaussian surfaces around charges to find the electric field strength at a particular distance. So let's say we have a point charge right here that has charge Q on it. Just write it. And let's say that we put a cubic Gaussian surface around that charge. And we want to find what the electric field strength is at any point along the surface of that Gaussian surface. Well, what you want to do is, of course, use the Gaussian equation, the Gauss's law equation, where you have the surface integral of E dot dA equals to Q inside divided by epsilon sub 0. Q inside is simply Q, epsilon sub 0 is our constant. But now what about the E dot dA? Now notice that the direction of the dA will always be perpendicular away from the surface, and of course as you get to certain points on the surface, the electric field will be away, radially away from the central charge. And you can see now that there's going to be an angle between them. Let's call the angle theta. So what I did was I took this surface right here, I folded it up like this. Here's our charge at the center. Now we're looking from the center of the cube towards one of the faces. And of course, it wouldn't matter which face you look at, you get the same kind of idea. This is the central point of the face, directly above the charge. And so you can see that this line from there would be perpendicular to the surface. Let's pick a point away from the center, this point right there. And so let's try to find the distance from the charge to that point on the surface. Now notice that the distance from there to there, I called it A. A would be half the distance from the distance from the central charge to the side in any direction. So from there to the front face, from there to the bottom face, from there to the out face is A. So that's this distance right here. And so trying to find this distance over here, notice that we have a distance x away from the center in this direction and a distance y away from the center in this direction. So this here, this line across here would be x squared plus y squared. There we go. And then you notice also that this diagonal distance here is the square root of a squared plus x squared plus y squared. So that would be the diagonal distance right here. That would be the distance from the charge to any random spot on the surface. Now, the electric field strength at that point would be equal to K times Q divided by R squared. And R squared, of course, is KQ over this distance. And of course, we have to then square that like that. So you can write this as K times Q divided by a squared plus x squared plus y squared. That would be the strength of the electric field anywhere on the surface or one of the faces of that cube. So now also realize that the integral E dot dA would give you the flux, the electric flux going through the side. And since there's 6 cubes and each cube is the same distance away from the central charge, each phase would have 1/6 of the total electric flux through that. So we can assume that the electric flux through one of the faces is equal to 1/6 the electric flux total, electric total. So that would be electric through one of the phases would be 1/6 the total flux going through all the sides. All right, now what we want to do is we want to go ahead and calculate what E dot dA is. Well, we know that E dot dA, or E times dA, is equal to E times dA times the, and of course I do it like this, times the cosine of the angle between them. Now how do we find the cosine of the angle between them? Well, let's see here. The definition of the cosine is equal to the adjacent side divided by hypotenuse. So that would be the ratio of the adjacent side divided by the hypotenuse. And here you can see that the adjacent side would be A, and the hypotenuse, of course, would be this quantity right here. So we can write this as A divided by the square root of A squared plus x squared plus y squared. That would be the cosine of theta. So we can write E dot dA times the cosine of theta equal to, E, of course, would be equal to this quantity right here. So it would be K times Q divided by a squared plus x squared plus y squared. dA, that's a small little area element right here, simply would be dx times dy. So it would be dx times dy. And the cosine of theta would be equal to a divided by the square root of a squared plus x squared plus y squared. Okay, that would be E dot dA. And if we now want to integrate that, so the integral of E dot dA would be equal to the integral of this. Now notice that A is a constant, K and Q are constants, so this could be written as the double integral, or the surface integral, I should say, the surface integral of, well, let's see, let's get the constant out first. That would be K, Q times A times the surface integral of dx times dy divided by the quantity a squared plus x squared plus y squared to the 3/2 power. And now this would then become a double integral over the x and the y to integrate over the entire surface. And of course, we know that this is equal to the flux through the surface, so that would be equal to 1/6 the total electric flux emanating from this charge. So that would be a total electric flux. And then, of course, from Gauss's law, we know that the integral, which is equal to the electric flux, in this case, the one of the surfaces would only be 1/6 of the total flux, would be equal to Q inside divided by epsilon sub naught. So notice that if you're trying to find the electric field strength using this right here, you're going to be up against a very difficult integral. You don't want to do that. If you're going to draw a Gaussian surface, always draw the Gaussian surface in such a way that the electric field emanating from a charge will be perpendicular to the surface no matter where the surface is, and therefore spherical surfaces or cylindrical surfaces are the way to go with a Gaussian surface. So here I would say, don't go this route. Don't use cubes, don't use rectangles, don't use boxes, just use spheres and use cylinders, and you'll like Gaussian law a whole lot better.